Good afternoon. So there's a midterm on Monday, and I noticed that not a whole lot of people are at B-Space yet, which is uncommon. Usually many more people are at B-Space that short before a midterm, so you must be very busy, and you have to start talking to each other. How does this go? How does that go? And so it will come soon. Or you know it all. Maybe that's the solution. Everything I discussed until Friday, and everything I gave you to read in the book, you need to know until Friday. Everything which is discussed on Monday will be part of the final, okay? And the final will be a little bit heavier on the last quarter of what we are doing, and then the summary of all three midterms, of the subjects of all three midterms. I would say, I don't know, some good mixture of that, all right? So it will be comprehensive. Now, the last time, another thing. Due to popular demand, I have added another office hour today from 4 to 5. They will be from 5 to 6, so 2 hours office hours. And the people who are done at 5 o'clock, they have to leave then to make room for the people at from 5 to 6. So come early or come right in there. You know the deal. All right, so that is always very pleasant for me to see you all working there, and maybe not so pleasant for you to stand there like herrings and soaking up all the information because it's very crowded in my office. But that's what it's called, office hour. Otherwise, I could give a lecture, then I would call it lecture hour. All right, without further ado, we have talked about Mr. Le Chatelier. Last time, Le Chatelier's principle. When we have a system in equilibrium and we do something with that system, we subject it to some kind of a change or stress. If you subject it to some kind of change or stress, then it will react in the direction that tends to reduce the stress. So if you look at that equilibrium reaction here, and this would be an equilibrium, the constant is K, is 6.8, it's larger than 1. What does this tell you? It tells you that the reaction is product oriented. It will make more product, it will like to make product, because the quotient K, or the reaction quotient Q, in equilibrium we call it K, is the concentration of N2O4 divided by the concentration of N2O. Since we have gases, we're using partial pressures, so this is the partial pressures of N2O4 divided by the partial pressure of NO2 squared, because we have here 2. So if K is larger than 6.8, that means you have higher partial pressure here than here, and in every case you have K larger than 1, that means you are product oriented. That reaction tends to make products. And so in this case, we also know that it's exothermic. That means it has a negative sign. That means that heat is generated in that reaction. And heat, you can look at heat that is generated in a reaction as a product. Okay? Now, if you take away, for example, this reaction, you take away some N2O4, you just pull it away from the reaction. Then what happens? This reaction is out of equilibrium. Okay, now K is not equals Q anymore. Now your Q is much smaller than K, because then you calculate this once you have taken something, an amount away from here, you calculate the new Q is N2O4 partial pressure. Since you have taken some away, the partial pressure is smaller, and divided to that partial pressure, and with this you see that you are not in equilibrium. And in order to get back into equilibrium, the reaction will continue and makes more N2O4 until it's back in equilibrium. Now, if this is an exothermic reaction like this, you also can look at heat as a reaction product. So if you take heat away, that means you cool it down. That means you drive the reaction to the right towards the product. Now, if you add heat, what happens then? You increase this amount here, because heat is a product, you increase this side here, so you're driving the reaction backwards towards reactants. And if you have here, for example, it's an exothermic reaction, you drive it into this direction. Okay, if you add heat, and if this would be a different reaction, and this would be exothermic, heat would be a reactant then, and if you add heat, then you drive it towards the product. Okay, this is not for this reaction, this is a hypothetical case, because we know this reaction is exothermic. And you have seen here, in equilibrium, Q was equal to K. So it was in perfect equilibrium. And now I doubled the volume. And you see this NO2 are the brown molecules, and N2O4 are the colorless molecules. They're white here. So I doubled the volume now. If I double the volume, what happens to the partial pressure? I have the partial pressure for both of the reactants. If I have the partial pressure, so I'm out of equilibrium. All right? So I can now calculate the new Q. And the new Q we did is 1/2 the partial pressure of N2O4 divided by 1/2 the partial pressure of NO2, since we have 2 moles of this squared. All right. Now, remember, Q was 2K then in this case, because this cancels, that half cancels here, and there's 1/2 stands here, and you bring this over, then Q is 2K. And this is not equilibrium. Q equals K is equilibrium, but Q equals 2K is not equilibrium. So what happens? You have to make more stuff. And what you make, if you do this, you have, if Q is larger than K, that means K is too small. So you have to go into this direction here to make more N2O4, that your K becomes bigger again, and that your Q becomes equal to K, that becomes bigger. Are you with me? It's very important that you understand that. It's not easy, but actually once you get the hang, it is easy, like with everything. Okay? All right. So then we talked about a specific equilibrium, the Haber-Bosch synthesis. This guy Haber, Fritz Haber, he was a physicist, a physical chemist, and he got filthy rich with this invention. Bosch did actually all the work. He had the idea. And you have nitrogen, gaseous nitrogen is used by man. Plants need nitrogen, but they don't take it up through their, not like oxygen, like carbon dioxide through their leaves. They take it up through the roots. And so the nitrogen in the air is 20%. It's not very helpful to have this. So you have to make another gas to make a compound, and the compound you can then react with some water, for example, or ammonium nitrate or some nitrate, then it precipitates, not with nitrate, with some nitric acid or sodium nitrate, then it precipitates as ammonium nitrate, and you can use this as fertilizer. The problem with this, of course, is that's an exothermic reaction, and at 25 degrees, there's not much going on here in terms of product. And so if you heat it up here, then you drive this even more to the left side. So that's a big dilemma, and they solved it by increasing the partial pressure to very high partial pressures of 200 atmosphere, and they raised the temperature to 500 degrees. So that's how they found a compromise, that they make enough of this ammonia that it then can be converted to ammonium nitrate, which is used as fertilizer, and you can put it out in the field. And then we talked about multiple equilibria. I know equilibrium A is an equilibrium with B. I have an equilibrium constant. The equilibrium constant is B over A concentration, and the enthalpy of reaction, the change in enthalpy of reaction is delta H1. Then I have another reaction B makes C. Okay, C is an equilibrium with B, and B is an equilibrium with C. So the constant is C concentration of C divided by concentration of B, and the reaction enthalpy for that reaction is delta H2. So now I have a reaction A goes to C, and this is an equilibrium, and this is a K3, and I want to know what is that K3, and I want to know what is that delta H3, so the heat of reaction for that reaction. So I write that K3 is C over A, okay? But now I can say, C, I can express here C over B, C over B is this here, that would be K2 here, okay, and this is, what is that here? A is B over A is this here, that's K1. So if I multiply this K1 times K2, exactly because this cancels here, I get C over A. With this I have K3 equals K1 times K2. That's that simple. And the enthalpy of reaction for this is just the addition of the two. That's a Hess cycle essentially. That's the addition of the two enthalpies of this reaction, because they're multiplicative, so they are additive here, all right? So let me see if you understood what I just told you and what I told you the last time, and let's warm up a little bit. So we have nitrous oxide, and you know everything about nitrous oxide here, and you have actually been asked that question the last time, so everybody needs to have this right now. Nitrous oxide is this brown colored gas, and this dimerizes to N2O4, which is colorless. So now I'm raising the temperature on this. I'm raising the temperature to a higher fixed temperature. What happens to the color intensity once I have reached, or this reaction has reached the equilibrium at that higher fixed temperature, okay? So you know everything about the reaction. You can say the color increases, the color decreases, that means more N2O4 is made, or there's nothing going on with the color, you try to trick us again, all right? Please think about it, and be quiet, think about it for yourself. I'd like to see where you are at this moment. And that would be also good for you if you know where you are. I'm not trying to be arrogant or facetious. I'm just trying to help, essentially, you know. We had this the last time, so if you have a good memory, you don't have to know anything, actually. Yes, good, excellent. All right, so you got the concept. That's very helpful for all of us. And so, of course, this is an exothermic reaction here. That is, heat is a product, okay? You raise the temperature, so you put more product in here. With this, you shift the equilibrium to the left side. It makes more brown stuff at this higher temperature, more NO2, and this increases the color intensity, and this is absolutely correct. So now, there you go, and it goes to this, so the partial pressure of NO2 increases, and with this, the color increases also because NO2 is right nasty brown, right? So now let's look at this one more time. So we know that this is exothermic. If I increase, so I can write here an equilibrium constant. Okay, you know how to do it. You can write a quotient. I can also write the equilibrium constant. You can look those equilibrium constants up at certain temperatures. And I write the equilibrium constant, and now I say, now what happens to the equilibrium constant if I increase the temperature of that reaction? Okay, so heat is a product, so I push that equation into more reactants. So my equilibrium constant is N2O4. Let me get back into equilibrium. My equilibrium constant is the partial pressure of this divided by the partial pressure of this here. So this here gets smaller, and this gets larger. With this, your K is what becomes smaller. Is that right? Okay, with increasing temperature, and this is what you see here. This is your K as a function of temperature. As you increase the temperature, your K decreases because you're pushing the reaction towards the reactants. And with this, you have a smaller K. Now, if it would be endothermic, that would be, the heat would be here. Not this reaction. If you have a reaction that is endothermic, the heat is a reactant. And with this is, if you put more heat in there, so you're pushing it, not this equation here, of course, but generally, you're pushing it towards the right side of the equilibrium. And that means you have more in the numerator and less in the denominator, with this K getting larger as you increase the temperature. And this is shown here. That would be an endothermic reaction. The temperature dependence of the equilibrium constant for an endothermic reaction. Okay? So let's do this here. I have not done this the last time, so I don't want to deprive you. Okay. So what we have here, the old joke, welcome Beijing, welcome Los Angeles. And so I have hot water here, and I have cold water here. So what should happen to the colors of those? This one should get, the cold water should get darker or lighter? Lighter, and this one? Darker. Okay, let's do that. There's a lot of buoyancy here. Okay. Now this is, you don't see anything yet, but yeah, there's already some change coming, hopefully. Let's see if this cools off. Yeah, I can see already. See some color changes? Yeah, clearly, even on camera there. Exothermic reaction, okay? Goes up in temperature, K goes up. No, K goes down, you're making more reactants. And in this case, you're making more product, okay? Because you remove the heat. So it's exothermic heat is a product, you remove product, but this is, I'm out of equilibrium, I gotta make more N2O4 to get back into equilibrium, okay? That's the easiest way to understand that. And you see, it will be never totally colorless because of the equilibrium. That also is the point, that you are not, for example, with delta G, if you look at delta G, let's do this right now. If you look at delta G, for example, for this reaction, delta G for this reaction here is, let's see, that can be, if it's spontaneous, as we have written it here, then delta G is smaller than 0. Delta G at standard state is smaller than 0, okay? If it's non-spontaneous, as we have written it here, then delta G naught is larger than 0. And if it's in equilibrium, it's delta G equals 0, okay? The same, so if you have, if it wants to go into this direction here, spontaneous in this direction, delta G is smaller than 0. And this means the sum of the free energies, Gibbs free energies of formation of the products minus the sum of the Gibbs free energy of the reactants. Don't forget the stoichiometric coefficients to put into there. Anybody heard? No, okay. Don't forget to put this thing, that was a serious question actually, not a joke. If you put this in here, then you see that it goes to the right side, okay? If this is smaller than 0, it goes to the right side. That doesn't mean that you don't have A and B, some A and B left over, and some C and D, but you have, it goes more into this direction. There's probably very little left and here and more left of here, okay, at the equilibrium. So it doesn't mean that it's totally only on the right side, it's an equilibrium. It's between back and forth, it goes back and forth. And it does this until it gets in equilibrium, delta G is smaller than 0. Now, let's look at K. So K, if this is large and this is small, then K is what? K is larger than 1, isn't that right? Okay. And this is large, so I take the quotient of this over that here. If this is small and this is large, then K is smaller than 1. Okay. And if K is smaller than 1, you are more reactant-oriented, that reaction. Okay. If K is larger than 1, you are more product-oriented. Okay. And we say so in slang, the equilibrium lies on the right side. Of course, there's no equilibrium lying on the right side. Equilibrium is on both sides. Okay. But it's more, if I say it lies on the right side, it means it's more product-oriented. Okay. That means the K is larger than 1. Are you with me? All four of you. Okay. All right. So now we see that there's a certain relation between K and delta G naught. So this is, of course, this hypothetical standard state. It's 1 atmosphere. Everything is at 1 atmosphere. This would be at 1 if these are gases. This would be at 1 atmosphere. This would be at 1, and this would be at 1 atmosphere. But this, we can see what the direction of change is. You know, this is our base system for comparison. And so if this would be were solutions here, this would be at 1 molar, this would be at 1 molar, this would be at 1 molar, this would be at 1 molar. Okay. So this is our reference system, and it tells us what direction the reaction will go. So now we can marry this. Here we know that delta G, everything's written here already. Okay. Delta G. Now let's talk about this. Okay. So when delta G is smaller than 0 and K is larger than 1, then it's a spontaneous reaction. Okay. Because delta G always has to be smaller than 0 for this to go product-oriented. And if it's product-oriented, K got to be larger than 1. So if you have delta G is larger than 0, delta G not in standard state, is larger than 0, and K is smaller than 1, K smaller than 1 means we have more of this stuff here than compared to this here, then it's not spontaneous in this direction. It's more product-oriented, and it is probably going spontaneously in the opposite direction. No, it's not probably. It is going spontaneous in the opposite direction. So now we have the third case. When delta G equals 0, delta G not equals 0, then K is 1, and this would be in equilibrium, but that would be at standard state, okay? At standard state, it would be in K equals 1, but it's very difficult to find a K of 1 at real conditions, okay? Because everything would have to be at 1 molar to find a K of 1 here, or at 1 atmosphere. And of course, if you have a real system that you let come to equilibrium, but you can't predict it with this delta G naught. But if you have this really, then the K is of course not 1. So there's a concentration on the right side, two concentrations on the left side, and it's very unlikely that it's 1. It's a very highly unlikely case. So we say now delta G naught is minus RT ln K. Delta G naught is minus RT ln K. So this is how I marry these two guys again here. And I say delta G naught is minus R is the constant, you know that, temperature in Kelvin, and the natural logarithm of your equilibrium constant. So if I give you the equilibrium constant, you could, for example, calculate delta G naught. Okay, because you take the logarithm of that equilibrium constant, multiply it with minus the natural logarithm, multiply it with minus RT, and if this is negative, then the reaction is spontaneous. If it's positive, it's non-spontaneous. Okay, and if it equals 0, then it should be 0, the delta G. Okay, now this is one thing. Now I want to make a different relation. No, not really. I want to take, if I just take K here, that's simple math here, I take K, that's the exponent of minus delta G naught divided by RT. Okay, that's a simple math which you all know from high school probably. I hope so. And so let's talk about this a little bit more. So we have delta G naught and K for this here liquid water and gaseous water at 25 degrees. Okay, so if you have liquid water here, does this automatically boil when you have this sitting here? No, okay. So you know now what delta G is probably. And what do you have more in concentration at 25 degrees? You have the gaseous water, so the steam on top of it, or you have the liquid water. So now you can tell me what are delta G naught at K for 25 degrees. For 25 degrees, and not the pressure that you have at 25 degrees, not 1 atmosphere, the pressure that you have at 25 degrees. So why don't you think about this and try to answer that? Most of you know what the pressure at 25 degrees is. I said it many, many times, I think. It's definitely not 1 atmosphere, okay? Will that be a spontaneous reaction at 25 degrees? What is it? What is it? Okay. Excellent. Very good. I think we need to discuss this nevertheless. So let me give you, because I want everybody to really understand that. So we have water sitting on water. 25 degrees is a standard temperature, all right? But the standard state is 1 atmosphere of partial pressure, okay? So you have this sitting with 1 atmosphere of partial pressure on top of it. What would it make at 25 degrees? You have 1 atmosphere of partial pressure of gas on top of it. What would it make? It would condense, wouldn't it? It would not boil. It would condense. It would go into the solution. Okay, that's the first thing. And so if you have, for example, sitting here a glass of water, and eventually it will slowly evaporate. But there is a partial pressure on top of the glass of water, and the partial pressure is relatively small, and it's constant. Why water evaporates is because we have all this air here, it sucks up the water, and so it disturbs the equilibrium, so it will make more gas in order to be with this low partial pressure in equilibrium with the water at 25 degrees. Okay? So this is why water evaporates. If I would have this in a closed system, that the surrounding here cannot suck up the water vapor and take it always away from the equilibrium. So what would happen here, I have this vapor pressure on top of it, and now this is taken away by the surroundings, because we have this larger room here, and this is why water evaporates. So it has to make more, because the equilibrium is constantly disturbed. All right? That's why if you have water sitting here long enough, it will evaporate. But it still has always the partial pressure of that gas, of the low partial pressure of that water vapor. You can see it, of course, because it's not boiling, that water vapor on top.